talk is Nima, who's going to tell us about thin trees and interlacing families on strongly related distributions.
So hi everyone. So this talk is about some combinatorial conjecture about the existence of something called thin trees in graphs. I'm just giving this talk in this workshop, even though it's based on a very old result. I'm just giving it to demonstrate a method for using polynomials to go beyond things you can do using randomized round. So let me actually give you a brief introduction. I know that we've gone over this in the boot camp, but let me just give you a brief introduction on the rough ideas in the method of interlacing families. The way I think of interlacing families is as some sort of a generalization of the method of conditional expectations. Okay. So this is like the most this is one of the most used facts throughout, I guess, mathematics, that if you have a collection of things, then there's always so if you have a collection of numbers, there always exists a number that's smaller than the expectation, right? But here is maybe a little bit more advanced version of this fact. If you have a collection of fractions, then there always exists a fraction, which is, so these are positive numbers, both in the numerator and the denominator. There always exists a fraction which is smaller than the expectation of the numerators divided by the expectation of the denominators. Okay? So both of these are true. And if you want an algorithm that finds the number or the fraction promised by one of these two facts, if you're dealing with like an exponential family of things, what you can do is you can use the method of conditional expectations. You can form a tree, basically. So in each step, you're basically partitioning your collection into two sets, and then just computing the expectation or the expectation of the numerators divided by the expectation of the denominators, and then there always exists a branch in the tree where this expectation is getting lower, right? So if you start from the top, you can always traverse down, and then in the leaves, you'll find the promised thing that's bounded by the expectation. So the method of interlacing families, so you can basically see all of these as an instance of the method of interlacing families. Okay? So if to each of the elements in your collection, you associate a degree 1 polynomial, so bx minus a, then this polynomial has root exactly as over bs, right? And basically, instead of computing these fractions and chasing them down the tree, what you can do is you can look at these fractions as roots of polynomials and then chase the roots down the tree. Okay? So the method of interlacing families is basically a generalization of this whole idea to polynomials of higher degree. Okay? So if you have a bunch of polynomials and you're taking their expectations, as long as some conditions are satisfied, you can again chase down the tree and find an element in the leaves whose roots are bounded by the roots at the top. Okay. So what Marcus Spillman and Srivastava, so when they basically pioneered this method, one of the key things that they observed was that for this to work for polynomials of higher degree, not degree 1 and degree 0, you have to have that the polynomials in this tree are real rooted. And that's pretty much the only thing that you need for this to go through. Okay? So as long as the polynomials at all of the nodes of this tree are real rooted, and as long as convex combinations of siblings are also real rooted, then the whole thing is true. That there always exists a leaf whose roots are bounded by the roots at the top. So we are going to use basically this method to prove some things about the combinatorial conjecture. So let me tell you about the combinatorial conjecture. So the conjecture is very simple to state. You have a graph G. What you want to find is a tree which is thin with respect to the graph. What does thinness mean? Thinness means that in every cut, in every way of partitioning the vertices into two sides, the tree must have at most an alpha fraction of the edges in the graph.
In the cut.
In the cut, yes. So you look at the edges of the tree and edges of the graph in the cut. The tree edges must be at most alpha fraction. Okay. So that's just a definition. There is so you could look for something stronger. You could look for something called a spectrally thin tree. So a spectrally thin tree is basically a stronger guarantee. It's a spectral guarantee. It's saying that if you look at the Laplacians of the tree and the Laplacians of the graph, then the Laplacian of the tree is bounded by alpha times the Laplacian of the graph, right? And just to make sure that everyone is on the same page, let me just tell you what the Laplacians are. So if you have an edge in a graph, a Laplacian of the edge is an n by n matrix. So this is n, which has exactly 4 non-zero entries. And the rest of the matrix is zeros. So these are the 2 endpoints of the edge E. And for a graph, the Laplacian is basically the sum of the Laplacians of edges for all edges in the graph G. Okay. So spectral thinness is a condition that's stronger than normal thinness, and this is because Laplacians capture the values at the cuts. Okay. So if you have basically a cut, then this is true. If you look at the quadratic form given by the Laplacian on the vector, the indicator of the set S, this gives you exactly the number of edges in the cut. So if you have spectral thinness, then that implies normal thinness. Now, so the conjecture, which I'm going to talk about, is about the existence of these thin trees. Okay, and the conjecture is basically saying that the obvious necessary condition is also almost sufficient. Okay, so what's a necessary condition for the existence of a thin tree? Well, if you're going to have a tree which is, let's say, 1 over k thin with respect to a graph G, then it better be the case that the graph G has at least k edges in every cut, right? Because the tree is going to have at least 1 edge in every cut. So this means that the graph must have at least k edges in every cut. Right? If you're 1 over k thin. Godin's conjecture is that this is basically sufficient up to a constant factor. So, all right, so let me tell you a little bit about the history of this conjecture. So it's known that this conjecture has strong implications for the asymmetric traveling salesman problem. So basically, if you prove this conjecture with a loss, which can be a function of n, if you prove that being kh connected implies f of n over k thin trees exist, then it implies that the linear programming relaxation for the asymmetric traveling salesman problem is tight up to a factor of f of n. Okay. Now now this is not that relevant anymore because Svensson, Tarnowski, and Weg showed that independent of thin trees, this linear programming relaxation is always tight up to a constant factor. Okay. But nevertheless, their method bypassed thin trees, so the conjecture is still open. The conjecture and the existence of thin trees is still open. Okay. So the first time that you see this conjecture, the first method that you might try to use is to basically look at what random spanning trees look like, right? So maybe you have concentration phenomena, and random spanning trees satisfy some sort of thinness with some loss, maybe. Okay. So that's exactly what Asatpur, Gomez, Madri, and Ovaiskaran and Saveri did. So let me tell you briefly about what you can get using randomized rounding. So k-edge connect having a k-edge connected graph implies that you can always choose a measure mu on spanning trees. Such that the probability that each edge basically is selected in your collection of spanning trees is bounded by 1 over k. Okay? So there exists a measure on the spanning tree such that this is true. You can actually take the measure to be basically the uniform distribution on roughly k trees. There exist about k edge disjoint trees on every such graph, right? So if you have such a measure, then the expectation of the value of the cut is good. So in expectation, your tree is going to be thin, right? So so you have this expectation is at most of 1 over k times the size of the cut. Okay. Now, if you have concentration of measure, then maybe you can expect that maybe for all such cuts, you wouldn't be too far from the expectation. So turns out that you have to work with special distributions because you can't hope for concentration on every distribution. So there exists a very special kind of distribution. So there exists basically lambda e's. So this is a basically so there always exists a collection of edge weights lambda e, such that if you select the tree with probability proportional to the product of lambda e's, then so you can make sure that so you can make sure that you can choose weights on the edges, so that if you select a spanning tree according to the product of the weights on the edges, then you still have this condition that the probability of each edge being included in the tree is still bounded by 1 over k. And then these measures are sort of spread out. So what they proved was that for this, basically with very high probability, there exists the tree that you sample according to mu is going to have at most log n over log n times the value of the cut for every s. Okay. So we are going to work with this special distribution later on. But that's what you get from just random spanning trees. Okay. So any questions so far?
Should there be a K?
Sorry?
Oh, there be K there.
Oh yeah.
How do you recognize if it's a good guy?
How do you recognize if a tree is a good guy? That's actually a computationally, we don't know how to do it. So if, if basically you had a, so if instead of checking whether a tree is thin, you were checking whether a general subgraph is thin, then that would be the generalized sparsest cut problem. And we expect we can't solve it. So yeah, so one of the strange things about this problem is that you can't check thinness, but you still want to construct something that is thin. Okay. All right. So even though you can't check thinness of arbitrary objects, you can still prove that they exist. So the randomized method gives you log n over log log n. So in this talk, I'm going to tell you how you can go beyond this randomized construction and get log log or polylog log n over k. So this is the rough outline. So Godin's conjecture wanted to go from some necessary condition, connectivity, to the existence of thin objects. Okay? Now, if you look at spectrally thin trees, you can make sort of a conjecture on the spectral side. So on the spectral side, something which is necessary is some spectral form of connectivity that I'm going to talk a little bit more about. So for now, you can think of it as electrical connectivity, which means that think of basically your graph as a network of unit resistances. Now, if you put basically a battery on the two sides, on the two nodes of an edge, on the two sides of an edge, you can measure the voltage and the current, and if you divide them, you get the effective resistance between these two nodes. So it turns out that electric current is some sort of a flow. So I'll get to that a little bit later, but basically the necessary condition now becomes that the effective resistance between the two sides of every edge is bounded by 1 over k. Okay? This is actually a stronger condition than kh connectivity. So if you have the electrical connectivity, you also get edge connectivity. And then the spectral equivalent of thin trees is just spectrally thin trees. So you want a tree whose Laplacian is thin. And then you can ask whether or not the spectral equivalent of Godin's conjecture is true. And that's a statement that follows from the work of Marcus Spielmann and Srivastava and the follow-up of Harvey and Olver. Okay? So just to make things clear, we want to prove such a thing. We don't know how to. But we know how to prove the spectral equivalent of Godin's conjecture. And it is really an equivalent form because this is also like the obvious necessary condition on the spectral side. I'll tell you more about it. Now, you can also always jump from the stronger statement to the smaller to the weaker statement. If you prove that a graph has spectrally thin trees, then you can also prove that it has thin trees. But obviously, you can't go from the weaker assumption to the stronger assumption. So the main point of this talk is how to go from this weaker assumption to the stronger assumption by relaxing some things. All right. So like I said, the weaker assumption doesn't imply the stronger assumption. Here is an example. So this is basically a large graph. So think of k parallel paths on the top and k parallel paths on the bottom. And throughout the graph, there are k vertical edges going from the top to the bottom. So this graph is kh connected. But if the distances between these vertical edges are long, it is not k electrically connected. And roughly the reason is that if you put a battery on the two sides of one of these edges, it would take a lot of energy for the electrical flow to go and use one of the other vertical edges. So if the distances are basically long enough, the effective resistance between the vertical edges, between the endpoints of vertical edges, is almost 1, close to 1. Now, I told you that electrical connectivity is actually a necessary condition for the spectral version. So let me just quickly tell you why. So the effective resistance, you can basically write it down in terms of the Laplacian of the graph. So for a graph, there is this. You can form this So you can, so for every edge, BE, you can form this n-dimensional vector, which is 1 at one endpoint of the edge and -1 at the other endpoint of the edge. And now BE times the Laplacian pseudo-inverse times BE. This gives you exactly the effective resistance of E with respect to G. Okay. So it is some quadratic form of the inverse of the Laplacian evaluated at some point. Okay. So if the Laplacians of the tree and the graph are comparable, if the Laplacian of the tree is bounded by alpha times the Laplacian of the graph, when you take the inverses, the Laplacian of the tree becomes 1 over alpha bigger than the Laplacian of the graph, right? So now when you evaluate it at this particular, evaluate the quadratic forms at this particular point, you get an inequality, which tells you that the effective resistance on the tree must be at least 1 over alpha times the effective resistance on the graph, right? But the effective resistance of any edge on the tree is exactly 1. Right? So this tells you that the effective resistance on the graph must be bounded by alpha. So that's a necessary condition. So this necessary condition, we'll see later on that it's sufficient for the existence of spectrally thin trees. Okay. So, but let me focus now on the more important issue, which is how do you go from the weaker assumption of KH connectivity to the stronger assumption of electrical KH connectivity. So the basic idea is that we can add things to our graph to make it more spectrally well conditioned. Okay. So what does that mean? So assume that you have you start from your graph G, which is KH connected, and you add a bunch of edges from a graph on the same set of nodes H. And you make sure that the graph that you add is not too crazy. You're not blowing up the sizes of the cuts. So in every cut, you want the graph H to be at most doubling, let's say, the number of edges. But let's say that after doing this, your graph becomes spectrally well conditioned, meaning that the effective resistances are now bounded by some alpha. Then you can use the spectral version of Godin's conjecture and prove that there exists a spanning tree in this H plus G, which is spectrally thin, and then therefore it is thin with respect to G plus H. So if you have something which is thin with respect to G plus H, it is also thin with respect to G, right? Because we didn't blow up the cut sizes by at most by more than a constant factor. So if you have a tree here, which is bounded by, in every cut, bounded by alpha times the value of the cut in G plus H, this is also alpha times the value of the cut in G. Now, if you want to use such a framework, there are obviously many problems. So the end goal is to make sure that H brings down the effective resistances. But one of the obvious problems is that if you bring down the effective resistances in G plus H, how do you make sure the tree that you find at the end doesn't use any edge of H? Right? That's one obvious problem. So the other problem is, so going back to your question, verifying whether such an H is not blowing up the sizes of the cuts is actually a computationally hard problem, right? How do we deal with that? Okay, so let me tell you how do we deal with the first problem, and that's making sure that the newly added edges aren't picked. So this is the statement I told you, which is the spectral equivalent of Godin's conjecture. If you have a graph and its effective resistances are bounded by alpha, then you have an alpha spectrally thin tree, right? So if we apply this to G plus H, we could the tree that we get could be using the newly added edges. So instead, we have to prove something stronger. So we have to prove that if you have a special subset of edges, so this would be the subset of edges from the original graph, F, and if the effective resistance of the edges in F are bounded by alpha, and F itself is KH connected, then you can prove a thin tree inside of F. Is the difference between the two statements a little bit clear? So the assumptions here are basically both weaker and stronger. So so it's weaker in the sense that for the edges inside of F, you want the effective resistance to be small, but it's also stronger in that you want F to be KH connected. You don't want the whole graph to be KH connected. You don't just want the whole graph to be KH connected. So let me tell you a little bit about why this is related to the method of interlacing families. Is it okay to raise this? So if you've seen Caddison-Singer and the method of interlacing families before, you might be familiar with such a statement that let's say these are the Laplacians of the edges that we have, L1 through Lm. So these are all rank 1 PSD matrices. Right? So the condition that the effective resistance is bounded by alpha is equivalent to saying that Li, it's equivalent to saying that Li is bounded by alpha times the sum of all of the Laplacians. Okay. So if you have such a condition, basically Marcus, Millman, and Srivastava showed that you can get a spectrally thin tree. But here we have this condition only for set F. On the other hand, what we know is that the set F is KH connected. Right? So by the statement that I just erased, there exists some distribution, mu, on spanning trees from F. Such that the probability that I is included into a tree sampled from mu is at most bounded by 1 over k. Okay. So the sort of statement that we want to prove now is that if you have such a distribution mu, then the probability that the sum of Li, I in t, where t is sampled from mu, this thing being bounded by alpha times the whole Laplacian, has positive probability. There exists something in the support of distributions that you have, which is thin with respect to the whole graph. So that's exactly the kind of statement we need from the method of interlacing families. So So if you look at the original method of interlacing families, basically, and Harvey and over, okay. So their method is basically you can think of it as the equivalent of this statement, where this distribution mu is basically a product distribution. So I'll come back to all of these later, but so the point is that we need some statement like this. We need some statement like that for distributions mu, which are a little bit crazy. They're not choosing edges independently of each other. They're just using a very actually strongly correlated distribution on the edges. Okay, so for now, let me shelve that statement. We'll get back to it in the second part of the talk. So let's say that such a statement is true. What do we do? So we still want to find something which makes sure that some k-edge connected subset of the graph, some k-edge connected subset of the graph will end up having small effective resistances, right? So the graph H that we're going to add to the set of edges that we're going to add, we need to make sure that it doesn't blow up the sizes of the cuts, and it's generally infeasible to check that. But here's a simple condition that would guarantee that you wouldn't blow up the sizes of the cuts. What if you use basically shortcuts? Okay, so let's say that the graph G that you started with was the gray edges, and the edges that you're adding are the highlighted edges in orange. Okay, if you can make sure that the orange edges are routable on the gray edges, so you can replace each one of them by a distribution on paths from the original graph, so that no edge is used more than once in total. Okay? So that would make sure that you're not using more than the original number of edges in every cut. Now instead of using these shortcuts, you can, if you don't care about basically being algorithmically checkable, what you can do is you can just write down an exponentially large convex program and put the constraints that in every cut you're not blowing up the size of the cut. Okay. So you put down basically variables for where you're adding the edges, and then the constraints would be basically that in every cut, the quadratic form of the Laplacian is bounded by the quadratic form of the original graph's Laplacian. Okay. And there is actually no need for you to be working with Laplacians at all. You can just add a PSD matrix to your graph, as long as you make sure that the value on these special vectors, on the indicator vectors of sets, doesn't blow up. Everything still goes through. Okay. All right. So you can basically write down. You can reduce the existence of. You can check whether such a PSD matrix exists by basically writing down a convex program. Okay. You just write down the conditions that you're not blowing up the sizes of the cuts. And then you also write down the objective, which is the effective resistance of the original graph's edges in such a convex program. So even though this is an exponential sized convex program and we can't algorithmically solve it, it's still useful to write it in this form, because you can use convex programming duality to analyze this mathematically and basically prove that if the graph is k-edge connected, maybe you can prove the objective is low.
Should that be ref sub G plus D?
That would be ref G plus D, but they're not that different. So if you replace basically D prime to be D plus G, then D prime is thin with respect to G if and only if D is. Right? So you can measure the effective resistance with respect to just D, and that's still fine. Okay? Oh yeah. So all right. So if such a matrix D exists, why can we use that statement over there to prove the existence of a spectrally thin tree? Okay. So the point is. So take the above statement, this statement. What you can do basically is that you have your original graph Laplacians, L1 through Lm, but you're also adding this matrix D, right? So the matrix D, there are many ways of writing this as a sum of rank 1 matrices. Maybe pick one. So let's say it's a sum of A1 up to some AT, right? So you add these rank 1 matrices to your set. So now you have A1 up to AT. Okay. Now you still let mu be the spanning tree distribution on original edges. Right? Which is going to satisfy the fact that the probability of every element being selected in it is at most bounded by 1 over k. So if the desired outcome happens, if there exists a basically tree such that the sum of Li is bounded by alpha times L1 to Lm plus A1 to AT, then you're done, right? Because now you get a spectrally thin tree with respect to your graph plus D. But then this means that for every indicator S, for cut S, the number of edges you have in the cut is at most bounded by O of alpha times the quadratic form of L of G plus D evaluated at the cut, right? And this is bounded again by O of alpha times the number of edges that you have in the cut. So if the desired outcome happens, then you're done, right? But the assumptions, if you look at the assumptions, okay, so this one is checked, but the other one, this one, is not necessarily checked, right? Because we have new things. We don't just have the original graph Laplacians. We also have to check this condition for AIs too, right? So we have to check. This thing divided by or times alpha. Right? But this is a trivial problem to solve, right? If you so this decomposition into rank 1 matrices was arbitrary, right? In particular, I can replace one of these AIs by k copies of it scaled by 1 over k, right? So I can just make AIs as small as I want, right? And eventually you're gonna make sure that each AI is bounded by the whole thing. The point is that AIs are never chosen in the distribution mu, so it's really so we don't really care about them that much.
Can you explain what you mean by effective resistance of D in D? And
Oh yeah, so it's just the same quadratic form. Sorry, yeah. So effective resistance of some edge with respect to D is just basically the same thing that you would write for Laplacians, except here with the inverse. Right. So the point is that if D is Laplacian of some graph G, then this thing is effective resistance in G.
And this is linear in the entries of D.
No, it's not. So you're taking D and you're inverting it.
So why is this a semi-definite?
Oh yeah, that's a very good point. So it's you can turn it into a semi-definite program. What you have to use is basically Schur complements. So there is so if you basically form this matrix like this, this matrix is basically positive semi-definite if and only if, as long as D is positive semi-definite, if and only if basically BE times D times this thing is it is upper bounded by T.
E.
Sorry, yeah. So you can make it into an SDP, but that's really not that important for this talk. All right. So now the question is, how do we analyze this convex program? Can we make sure that such a graph or such a matrix D exists that brings down the effective resistances? Okay. So let me give you a toy example first. So let's say that we don't care about thinness in every cut. Let's say that there is some special family of cuts, in particular degree cuts, the cut around every vertex, and we only care about thinness in these cuts. Okay. So let's call this degree thin tree. So we want to we have a graph G and we want to find another graph or a spanning tree of it T, such that for degree cuts this inequality is satisfied. Okay, so the degree of every vertex is bounded by alpha times the degree in G. Okay. So if we want to do this, we can make sure we only need to make sure that the D that we add doesn't blow up the degree cuts. Okay. So let me just say that there has been a lot of this problem is actually studied, finding trees that are thin in degree cuts, and we know very good bounds for it. But this is just to demonstrate this framework. All of these methods are more combinatorial and don't follow this. Okay. So is there a graph or a matrix D that we can add to our graph which doesn't blow up the degree cuts but makes sure that the effective resistances become small? Right? So the answer is that you can always add an expander to your graph and make sure that this happens. Okay. So what's the point? The point is that if you add an expander to your graph, you're not blowing up. So this is a constant degree expander. So let's say a 3 regular or k regular expander. So if H is an expander, is let's say a k-regular expander, then G plus H, its degree cuts are not blown up because the each degree cut of G was at least k. So this thing basically evaluated at S and S complement is at most twice G of S and S complement. For degree cuts S. But the Laplacian of the point is that the Laplacian of an expander is a very good approximation to the Laplacian of the complete graph, right? So L of H is spectrally similar to L of Kn times k minus 1, right? So then it means that the effective resistance of every edge with respect to h is bounded by O of 1 over k. This you can just prove for expanders, right? So if you didn't care about thinness and you only cared about degree thinness, this is how you would do it. Now let's go back to the original problem. Can we always find well conditioners for all cuts, right? So this is the same convex program as before. You can just try to analyze it. The problem is that even if you use convex duality and try to make sure that try to basically prove that this is bounded, you would find actually counterexamples. So there are actually KH connected graphs for which this is the answer to this convex program is basically constant. You can't bring down the effective resistances. So what you can do is you can again relax, and instead of trying to make sure that the effective resistance of every original edge is small, you can make sure you can basically find a k-edge connected subgraph of the original graph whose effective resistances are small. So the problem is that it's hard to make sure the effective resistance of every edge comes down. You can just again relax that and make sure that the effective resistance of a subset comes down. And that subset is big enough to support a k-edge connected graph. Okay. So let me maybe skip a little bit of this part. To make sure that you find such a KH connected subgraph, one strategy is to make sure that the average effective resistance in every cut is small. That would imply KH connectivity of low effective resistance edges. That's still bad news, but there are some strategies that you can use to deal with this. Since I'm running a little bit low on time, let me just skip these. So the end point is that you can find a hierarchical decomposition of your graph, and what you can make sure is that in this hierarchical decomposition, in every degree cut of the hierarchy, there exists at least omega of k edges whose effective resistance has been lowered. So now in each level of the hierarchy, you have a KH connected subgraph, and because you have a hierarchical decomposition, the entire thing becomes KH connected. So let me just skip this because I wanted to switch to the interlacing families part. So now let's switch gears entirely and work on this statement. So this is again the kind of statement that we want to prove, that if you have a bunch of rank 1 PST matrices and you have a crazy distribution on subsets of them, then the probability that for something, or there exists something in the support of your distribution which is thin. Okay. So the method of proving such statements is pretty much the same as what you would do with the original interlacing families proofs. So let me give you an overview of this. So if you remember, we had this tree in the beginning. So we had a tree in the beginning whose leaves were specific polynomials. So these polynomials are associated to spanning trees in our distribution. So there is P of T1, P of T2. And you have this crazy distribution that takes average of these things, and at the top you have expectation of t selected according to mu of pt of z. So this is the same tree we had in the beginning. So the way you build this tree is basically by conditioning on whether or not each edge is inside the tree or not. Okay, so this is so the nodes on here are basically t given mu, z, given that let's say one was in t, and this one is that pt of z, and that one was not in z. So this is for edge 1. Then you go down the tree again for edge 2, and so on. So the branching in the tree basically corresponds to your decisions about whether or not you should include an edge inside the tree that you're selecting or not. On the bottom, on the leaves, you have actual spanning trees. And what you need to do is you should put down polynomials here whose roots correspond to the thinness of the tree. Okay? So it's easy to put down these polynomials. So what you can do is you can form a determinantal polynomial. So the point is, if you choose your polynomials to be like this, then the max root of PTZ is bounded by alpha if and only if T is alpha spectrally thin. So so the original strategy of Marcos, Spillman, and Srivastava was also similar to this. You basically condition one by one on whether or not elements are inside your set S or not, and then what you have to prove is that first of all this is an interlacing family of polynomials, so meaning that all of the intermediate nodes are real rooted, and convex combinations of siblings are also real rooted. So then that would tell you that if you have a bound on the roots of the polynomial on the top, you can find something in the leaves whose roots are bounded. And then the second more important thing is to prove that the roots at the top are bounded. So again, similar to the original interlacing families method, both of these statements are proved by writing the polynomial at the top in a different way. So what you want to do is to prove that this thing is real rooted, where T is chosen according to this crazy distribution mu on spanning trees, right? And so here is the punchline that if this is the polynomial g of z, you can write g of z in this form. One minus fraction. Times let me parse that for you. So you have a polynomial associated to your matrices LE, right? In fact, each of those PT polynomials, you can write it as, so let's call this H of Z1 up to Zn. Right? So this is a polynomial that encodes all of those specific polynomials on the leaves as its specializations. So basically, PT of Z is just H of the all ones vector minus, or Z times the all ones vector minus the indicator of a spanning tree T. Okay. This polynomial is encoding your distribution mu. So it's basically this V mu of Z is the sum over all spanning trees in your, so it's, let me write it this way. So it's the expectation of T chosen according to mu of Z to the T. It's the same as the expectation of the product of edges in T, Z. So for each tree, you can associate a monomial, which is the product of the variables associated to the edges inside the tree. And if you take this expectation over the distribution on the spanning trees, you get a polynomial whose coefficients are basically capturing the probabilities of the probabilities given by mu to the specific spanning trees, right? Now the point is that this is a determinantal polynomial, so it is real stable. This also turns out to be a polynomial capturing a Strangeri-Rayleigh distribution. So it's the generating polynomial of a Strangeri-Rayleigh distribution, so it is also real stable. So once you take the product of two real stable distributions, you get a real stable, the product of two real stable polynomials, you still get a real stable polynomial. And these are operators that preserve real stability. So the reason these operators preserve real stability is that basically the polynomial y minus 1 minus y squared is real rooted. So it's a known fact that if you have a polynomial which is real rooted and you replace its variables by partial derivative operators, it is a real stability preserver.
But also because it can be factor 1 minus.
Sure, you can also factor it, and then it's basically saying the same thing. Yes, you can also factor this into 1 minus partial times 1 plus partial, and each of those would be real stability preserved. Okay, so the end result is going to I forgot. So at the end you also have to plug in basically ZE equals Z. So you have to symmetrize all the variables. So you start from two real stable polynomials, you take their product, you apply a bunch of real stability preservers, the end result is going to be real stable, and then you make it univariate. You plug in the same variable for all. So the end result is going to be g of z squared, which is real stable. But if g of z squared is real stable, then g of z is also real stable. So that's the proof that the node at the top is real stable. But then for other nodes, what you can do is you can just condition your distribution on the edge 1 being inside or the edge 1 being outside and so on. The point is that conditional versions of, if you condition a Strangeri-Rayleigh distribution, you remain Strangeri-Rayleigh. Okay. So everything still goes through, and all of the intermediate nodes also become real stable. So the other thing that you have to show to prove that the family interlaces is that you have to prove the convex combination of siblings is also real rooted. Okay? So that proves that basically siblings or sibling polynomials in this tree have interlacing roots. Okay? But if you take so there is one particular convex combination of siblings which we know is real rooted, right? So there is a convex combination of these two that gives you exactly this, right? But we have to prove that for every convex combination you get this, right? But if you choose a different convex combination, it's as if you're basically playing with the weight of the edge on the weight of edge 1 in your random spanning tree distribution. So if you play with that weight, you can get any convex combination of these two polynomials. Okay. And for all choices of weights, the spanning tree distribution, the weighted spanning tree distribution is strongly Rayleigh. So that proves that the family interlaces. And then the way that you prove the polynomial at the top has bounded roots is again by methods very much similar to Marcus, Spillman, and Srivastava. So can I go a little bit over or no? Yeah. So let me just give you the high level. So the high level is that you still have to introduce barrier functions. Barrier functions are basically derivatives of the log of your polynomial. Okay? So you prove that the derivative of the log of the polynomial here initially is bounded, and the derivative of the log of the product of these two polynomials is just the sum of the derivatives of each one. The derivatives of log of this one being bounded corresponds to the marginals of the distribution mu being bounded, and the derivatives of log of this one being bounded corresponds to the other condition we needed, this one. So initially the derivatives of the log of this polynomial are bounded, and then you can prove that after you apply each of these operators, you can basically shift your polynomial so that the derivatives of the log are bounded by what they were previously. So that's just the high-level picture of what's happening, and yeah, so that's how you prove such a statement. Let me just conclude. So what I gave you was basically a sketch of this fact that every k-edge connected graph has a thin tree, which is polylog log n times worse than what you would expect, or what the conjecture is. So there are obvious questions. One of them is, can we build these thin trees that we know exist efficiently using an algorithm? And this very much goes back to the question of whether or not you can make the method of interlacing families algorithmic. So the other obvious question is whether or not we can remove the dependency on n. That would have a lot of implications even for the asymmetric traveling salesman problem. So I gave you this toy example about degree cuts, right? What about other families of cuts? If you care about thinness with respect to some subset of the cuts, for what families can you get a tight well conditioner? Okay? And then finally, this method of interlacing families was originally invented for real rooted polynomials, right? What if instead of a real stable polynomial here, you have something which is not real stable but in the same vicinity, right? So can you basically extend this method to other distributions mu? In particular, can you prove an analogous statement when mu is a log concave distribution?
Meaning you want to prove that you will have real roots?
No. I just want to prove the conclusion of the statement that this probability is, oh sorry, this shouldn't be equality. That this probability is positive as long as your distribution mu has a log concave polynomial and as long as these two conditions are satisfied. So that would probably require you to go or to change something in the interlacing families method, and I think that would be an interesting exercise. So yeah, so thanks.
time for a quick question. Already over.
So if I understand correctly, like you showed there was this bad news which you got. So
Yeah.
does that mean like your approach cannot be used to remove log n, adding this D?
Yeah, so to basically deal with that bad news, we had to make compromises, and I didn't go over what those compromises are at all. But there are several places where log n shows up, and yeah, there are examples where the convex program you use at the end gives you log n, so it can't possibly go. The analysis is tight, basically.
But in principle, this approach of adding a suitable D could work.
I mean, it depends on what the end goal is, because if your end goal is to bring down the effective resistance of every edge down, then it wouldn't even work for log n, right? If you make the compromises on which subset of the edges you want to bring down, then yeah, could work. Yeah. So the statement that could be true is that there exists a subset of the edges, which is KH connected, and you can bring the effective resistance of all of them down to ball 1.
Losing only a constant.
Losing only a constant, yes.
Great. Well, thank you again, Mira.